Can you guys hear me well on Zoom? Okay, I'm gonna go ahead and get started. Thank you guys for coming to day 2 of the electrochemistry crash course. Today we're going to talk about electrochemical kinetics, and as well as review last week a little bit and go through the homework of last week. So a quick review, we talked last week about the thermodynamics of electrochemistry, including the relationship to the Gibbs free energy, the standard potential of a cell, the Nernst equation, which relates the ratio of the reduced and oxidized species to the potential that is the non-standard potential of a cell. And then we related the potential of the cell to the standard potential of a reaction at the cathode and the standard potential of a reaction at the anode. We looked at the example of zinc and copper, where we saw that zinc can be oxidized, releasing 2 electrons that moves through an external circuit and then comes over to another electrode that reduces copper. And we found that this is a spontaneous reaction and can be used to drive electrons through an external circuit. And if we had a LED or another light source here, we could turn on a LED. So I asked you all to do this, these exercises. I hope you did. If you didn't, that's okay. I won't judge you. So I asked you first to look up what is the redox couple of iron ferricyanide. I looked it up in the back of Bard and Faulkner, which is reported to be 0.361 volts versus SCE. You can find that probably on Wikipedia or many other places. So then I asked, what are the concentrations of the iron 3 complex at minus 0.5 volts, 0 volts, and plus 1 volts versus SCE? And then I asked you, what is the concentration of the iron 2 species at those same potentials? As you might imagine, predicting the thermodynamic value of these concentrations at various potentials can be quite useful. So remembering the Nernst equation, we know that whatever voltage we have is equal to the standard potential, which is 0.361 volts, minus 0.059 times the log base 10 of the ratio of iron 2 to iron 3. Doing a little bit of arithmetic, we can rearrange this such that the difference in the potential, the solution potential, and the standard potential divided by 59 millivolts is equal to the log base 10 of this ratio. We can raise both, take both sides raised to the 10th, set this equal to Q, and we know that the total concentration, as I mentioned up here, is 5 millimolar. We have the total is all of the iron 3 plus all of the iron 2. And then we can solve for iron 3 doing a little bit more arithmetic. Now, we can solve for Q using this equation here. again, we have all of the variables we need. We know the E0. And so if I put in, for example, minus 0.5 volts here, I can then solve for iron 3 in this equation. I can then solve for iron 2, taking the difference. And so I have that shown here. So at minus 0.5 volts, Q is this number times 10 to the minus 15th. So quite small. Basically, all of it's in the iron 2 state, which makes sense. We're more than a volt negative of the EU of the standard potential. And so very little iron 3 there. Again, even at 0 volts, most of it is in the iron 2 state. And then if we jump all the way up to 1 volt, we see that most of it is now in the iron 3 state. I wanted to double check my formula, so I put in 0.361, and indeed Q is 1 here. The iron 2 and iron 3 values are equal. Now I just did this all in Excel. You can set up a similar spreadsheet to do these calculations for you. The next thing I asked was to use a graphing program to plot the concentration profiles of these two on the same graph. And using the same formula, I took various points. We can see down here at reducing potentials, it's all in the iron 2 state. As we approach the E0, the concentrations become equal, and then the iron 2 state all becomes oxidized, and it all becomes in the iron 3 plus state. So that was just kind of to calibrate yourself on these potentials. Again, I mentioned last time that these kind of resemble a pH titration where it has this sigmoidal shape. Now again, these are all thermodynamic values. So in the next question, I wanted you to think a little bit about some of the mathematics. I suppose that for every oxidation state, we're going to add 700 millivolts. Now, this isn't always a good assumption. As we know, ionization energy depends on exactly which orbitals these electrons are coming from. But I wanted to make this supposition that it was going to be 700 millivolts for each additional electron that we take out of a metal. So if I make that assumption to go to the iron 4 plus state, the E0 of that would be 1 volt. And if I wanted to go to the iron 5 plus state, it'd be about 1.7, 1.8 volts. So quite oxidizing. Again, these are not values that you should take to the bank. This is just an exercise. But then I wanted to know what would the concentration of these be at 0 volts versus SCE. And if we take the same relationship for these new E0s that I've posited, we find that the values are somewhere in, the Q values are somewhere in 10 to the minus 17th or 10 to the minus 29th. If I look at a 1 molar solution of a 1 liter 1 molar solution, I know there's Avogadro's number of iron atoms. And so if I look at iron 4 there, the concentration of that would be somewhere around 1.2 times 10 to the minus 17th moles per liter. And there's essentially 0 iron 5. But practically speaking, neither of these are really there. There's very little of it, and certainly none of it that could contribute to any reactivity that you see. So moving on to something a little bit more practical. In electrochemistry, we typically see this 3 electrode arrangement. And as I noted last time, we use this reference electrode, which is some standard couple, for example, silver 0 coupled to silver chloride. And we use that because that potential does not change. And then when we measure the voltage of the cell, we can always report it versus a reference electrode that is unchanging. So then we can have the working electrode that does all of our electrochemistry and can become a useful tool. But I show this counter electrode. Does anyone have any idea or any guesses as to what the counter electrode does? Remembering that we want the reference electrode to stay at the same potential. People on Zoom can feel free to speak up as well. That's exactly right. It closes the circuit. So the counter electrode is the electrode through which current flows. If we flow current through the reference electrode, we would change the concentration of the redox species, and that would then change the voltage of the reference electrode. So the counter electrode completes the electrochemical circuit by compensating whatever current is passing through the working electrode. Now, in most cases, in any analytical chemistry, we don't care at what potential the counter electrode is. Maybe I have my working electrode doing some reaction at plus 1.5 volts. My counter electrode might be at minus 5. I don't know. Generally, I don't care. But generally, we want the reference electrode and working electrode as close together in solution as possible, so that the reference electrode and the working electrode experience the same electric field from the counter electrode. So reviewing a little bit from last week again, Faradaic reactions occur at the solution interface when we control the energy level of the working electrode using a potentiostat. And so when we change the energy level of this working electrode, we can cause electrons to flow to or from the solution. The thermodynamic description being shown here in the Nernst equation. And pictographically shown here, we have this energy diagram shown versus SCE. We could also show this versus a vacuum or different reference electrode. But as we scan the potential, if we go to a more negative potential, electrons from the electrode will eventually be higher in energy than some energy state of a molecule in solution, for example, and then transfer an electron to that species in solution. Alternatively, if we scan in a more positive direction, eventually that energy level will be lower than some species in solution, and an electron will be transferred from the species in solution to the electrode. We measure this current in amps or in coulombs per second, and through Faraday's constant, we can relate coulombs to number of electrons. The Faraday's constant is 96,485 coulombs per mole of fundamental charge, i.e. electrons. So when this electrochemical current flows to a redox active species, we call it Faradaic current. And it's what we typically want to measure. It's usually the current that we are most interested in. Now, last time I also mentioned we have this non-Faradaic reaction wherein ions from the solution interact with the electrode that we've placed in solution. Again, we can control the potential externally. And when we, for example, polarize in a positive direction, anions, negatively charged species from the solution, will migrate towards the electrode in response to the electric field. Alternatively, if we polarize in a negative direction, cations will flow towards the surface of the electrode in response to the electric field. We term this capacitance the double layer, then we call that the electric double layer. And And it acts similar to the parallel plate capacitor in many ways, in that there's a time response associated with it. Typically its current falls to zero quite rapidly. So if we connect a battery to two metal plates and we pass current, the charge will accumulate on the metal plates quite rapidly, and then we will have a static field. As I mentioned last time, this is termed non-Faradaic current, and sometimes you might hear about an ideal polarizable electrode, and basically an ideal polarizable electrode is an electrode that only allows non-Faradaic current to flow. So one big difference between electrochemistry and homogeneous electron transfer is that the species have to interact with the surface of the electrode in order to pass an electron. It's not like I have a metal salt dissolved in solution that can react with a different reactant dissolved in solution. We have to have mass transport to the electrode. So in order to properly understand the kinetics and the current response that we observe, we have to understand this mass transport. Now, migration we already talked about a little bit, which is, for example, the ions that move in an electric field in the non-Faradaic current for the double layer capacitor. And we often use an electrolyte at a very high concentration, or relatively high concentration, which minimizes the migration of a redox active species. So a common electrolyte in aqueous solutions would be potassium nitrate, typically 1 mole per liter. And then your analyte would be around 5 millimoles per liter. So you usually want 100 to 1,000 times more concentration of your electrolyte than your redox active species. Now that's not always the case. Sometimes you want to avoid an electrolyte, and sometimes if you're really clever, you can use your redox active species as your electrolyte. But typically in analytical chemistry, we want to avoid that. The next way that we can have mass transport to the electrode is through convection. So we can stir a solution. If we're evolving a gas, typically we want quite a high flux of solvent to remove bubbles from the solution. Or if we're doing more electroanalytical chemistry, often times a rotating disc electrode is used because we can rotate at different rates and control the flux of species to the solution in a very precise manner. The last way is diffusion, and I'm not going to go through fixed laws of diffusion, but essentially when we start an electrochemical reaction, diffusion will occur and the species will diffuse to the electrode, react with the electrode, and then the reactant will diffuse away from the electrode. And we'll see that a little bit more clearly when we get to the cyclic voltammogram simulations. So taking a look again at potential step voltammetry, let's consider a 5 millimolar solution of ferrocene dissolved in 0.2 moles per liter lithium perchlorate. So in acetonitrile, a common electrolyte could be something like lithium perchlorate if we're doing non-aqueous chemistry. Again, remembering the Nernst equation, we'll start the experiment at, let's say, 0 volts, and then as quickly as our electronics allow, we will jump to +1 volts at the working electrode. And so we might ask ourselves, what will happen? And so since I showed this to you all last week, what will happen? Or do we not remember last week? Say that again. Yeah, there will be a change of the species in solution. Exactly. So if we start with ferrocene in the 2+ state, at 0 volts, the thermodynamics favors ferrocene in the 2+ state. Again, that's more negative than the E0. If we all of a sudden jump to +1 volts, now we're more positive of the E0, and it favors the iron 3+ state. So we instantaneously jump, and all of a sudden we have a thermodynamic situation where the iron 3+ is favored. So the electrode will then begin to oxidize ferrocene to ferrocenium from iron 2+ to iron 3+ at the electrode. This will happen instantaneously, and then diffusion controlled kinetics will take over. The other thing that we need to consider is that as soon as we do this jump, we will have ions that will migrate to charge the double layer, this non-Faradaic current. So pay attention because this is on the homework for this week. So as I mentioned, the ferrocene to oxidation at the electrode will be diffusion controlled. We won't go through the full derivation of this, but you can do so. I recommend Bard and Folkman if you would like to investigate this a little deeper. But essentially, we can plot the current as a function of time. If we know the number of electrons that's transferred, in this case it's 1. We know Faraday's constant. You can Google that if you forget. 96,485 coulombs per mole. We know the area of the electrode, ideally. We know the initial concentration, the diffusion coefficient of ferrocene. Can look that up, or maybe at some point we might use this technique to measure this. Everybody knows pi, and then we have time in seconds. You might not be able to see this here, but this t is under the square root. So this evolves with the inverse square root of time. When we look at the non-Faradaic contributions, the double layer charging is an exponential, which is related to the voltage change, the series resistance or the solution resistance, and the time constant is in the exponential here. And so what we look at when we see this current, when we do the voltage step at time 0, so prior to this perturbation, there's 0 current flowing, but at time 0, we have both processes occurring. We have this Faradaic current shown in orange here, which is quite small actually relative to the double layer charging current, which is greater and is shown here. And this gray curve shown here is the linear combination of the two of them. So when we make this measurement, all we measure is the current and we see both. Now, because of the different dependencies on time, the double layer charging actually decays quite fast. And we see this blue curve coming underneath the orange curve here eventually. And then the orange curve decays much slower. And we see eventually this overtaking the total current. So at short times, the double layer charging is dominating current, but at longer times, Faradaic current is dominating the current. And so that's that will be on your homework. So that's something to kind of think about, and you'll see that quite often. If you're ever doing an experiment where you move to a voltage for some electrolysis or some reaction, you'll notice that at very short times you see a spike, and then it will decay to some steady state. And that spike is related to your double layer charging. And again, I mentioned that these are a combination of these two currents. So one of the most common techniques we'll see in electrochemistry is cyclic voltammetry. So in cyclic voltammetry, the perturbation that we apply looks like this, where we have some starting potential, we linearly move to some other potential, we stop and instantaneously turn around and scan back to another potential. Maybe it's the same one, maybe it's a different one. So we have the starting potential, switching potential, which would be this point here, and the stopping potential. The other parameter that we need to consider is the scan rate, which would be the slope of this, which is typically in millivolts per second or volts per second. If you're not sure, if you're doing an experiment, you're not sure what scan rate to start with, I recommend 100 millivolts per second, because that's quite fast and you have an idea of what you're looking for. If you want to get a more beautiful looking figure, maybe 20 millivolts per second is better. And then in certain cases, you might go as low as 1 millivolt per second, but we can talk about that a little bit more probably next week when we talk about bulk electrolysis. And so the plots that we have is the current versus voltage. And so we might plot several cyclic voltammograms with different scan rate, and that wouldn't be apparent from this plot. We could do different scan rates and they would have different characteristics on this plot, but it wouldn't be the same. So this is actually a three-dimensional plot where we have time on the z-axis and this is projected down. And as electrochemists, we kind of learn to read that, and you'll start to get a feel for what that will look like in your CVs. And again, as with the steps potential, both Faradaic and non-Faradaic currents are observed. So this is our typical CV duct that we see on a nice redox couple, and it has a few distinct features. So one is the peak current, which is the peak current of this wave. So in this case, we're scanning to more positive potentials and we're having oxidation. And so that is occurring at the anode. So this is I sub P comma A, which is the peak current of the anodic peak. And in the reverse direction, we're having a reduction process occurring. And this is I peak cathodic, IP comma C. This will be in your homework as well. I'll send out the slides, by the way, for last week and this week. That might help you, well, certainly will help with the homework because you'll need these equations. And it's dominated by this equation for a reversible charge transfer, where N is the number of electrons, A is the area of the electrode, D sub 0 is the diffusion coefficient, C star sub 0 is the initial concentration, and V is the scan rate. So a couple important features are that the peak current is actually linear with respect to the concentration of your analyte. So something to consider if you're having very small peaks that you can't resolve. It's linear with respect to current. And one very, very important feature is it's actually the peak current increases with the square root of the scan rate. So you can increase the scan rate, but it only increases to the square root for Faradaic current. The other important features that we consider would be the peak potential. So that is the potential at this peak current. So here it's the E sub P comma A. So that's the peak current on the anodic scan. And then on the reverse scan, it's the E peak cathodic. So in many software programs, you can plot this. Sometimes you can do it by eye. Sometimes you might fit the peak. another important feature is this delta E, which is the difference in peak potentials. And so for a reversible electron transfer, this delta E is 59 millivolts divided by the number of electrons. Now that can be useful because if you see that you do a cyclic voltammogram and the peak separation is 30 millivolts, you know this was not a 1 electron transfer. In fact, that's more likely to be a 2 electron transfer. However, more than 59 millivolts does not mean less than a 1 electron transfer. It typically is related to solution resistance, or it can be related to electron transfer kinetics that are more related to the reversibility of the electron transfer, which I'll explain further in just one second. And lastly, we have the E1/2, which is the half wave potential. There's often confusion in the literature about exactly how to do this. My preferred method is the average between the the peak cathodic current and the peak anodic potential for both of those. And that's often used to estimate the E0. If we have a new material that we've synthesized, a new molecule or a new organometallic, then we may not know what E0 is, but if it's electrochemically reversible, we can get a good estimate of what that is. Now, oftentimes, if this is not electrochemically reversible, maybe we only have one anodic wave. For example, if I have a species where it oxidizes and then undergoes some other chemical transformation and is not re-reduced at the electrode, oftentimes what is done is the background current and the peak current are, the difference is taken between the two, and you take the halfway point of the wave. So you would say, okay, at what potential am I halfway on the current? And that's the way you would estimate it still. That gets a little shaky, but that can be a way to estimate the E1/2 and the E0. So we have modern software that allows us to simulate CVs. And so I'm going to show you a simulation of ferricyanide using a software program called DigiElk. This is a software which we have paid for in the Galán group. Okay, so friends on Zoom, can you see two graphs?
Yes.
Okay. I think that was a yes. So what we have shown here on the right is our real-time potential versus current. And so for this species, we have iron 2+ and iron 3+. This is ferricyanide. We're starting with the, let's see if I can pull this over. So shown in black here is the concentration on the y-axis versus distance from the electrode. Okay, so here at this point at 0 is at the contact of the electrode, and this is a linear distance away from the electrode. Okay, but on the y-axis we're looking at the relative concentration. So over here at the bulk, I have, I believe in this simulation, 5 millimoles per liter of iron 2+, and at the bulk I have 0 millimoles per liter of the iron 3+. And what this is going to show us is the concentration profile as we evolve in this cyclic voltammogram. So we're scanning to more and more positive potentials, and you can see that we're starting to get current here. Simultaneous with that, we're starting to see a change in the potential here. Now this program or this simulation is set up such that the current profiles at the electrode match the Nernst equation. So in other words, the electron transfer is happening so rapidly that it's instantaneously reaching equilibrium at the electrode. And so as this anodic current flows, the iron 2+ is oxidized to iron 3+ at the electrode. And now we can see we have a little bit of iron 3+ evolving at the electrode. Continuing forward, we see the current continues to go up past where the E1 half is. We can see now we've moved even past halfway of the meeting point of these two concentration profiles. And then at this point, this now looks like what we might expect from a potential step experiment, where all of the iron 2+ that contacts the electrode is instantaneously oxidized to iron 3+ and then diffuses away. And so indeed, the second half of this wave is diffusion control. So we can continue to let that evolve. And then eventually we get to this point here, which is our switching potential, and it starts to move back in the other direction. And even though we're scanning back towards more negative potentials, we're still at a potential where the thermodynamically favored component is the iron 3+ phase. All of the iron 2+ continues to get oxidized. But eventually we get to a point around here where we're starting to change the thermodynamics. And there's no longer so much driving force for the formation of iron 3+, but we have a surplus of iron 3+, which then begins to become reduced. We start to have cathodic current flow as the concentration profiles of these two evolve. We reach a peak here, and then again at further times we reach back towards bulk equilibrium. So if we continue to scan that way or hold the potential, these profiles would eventually reach flat lines again. So we'll watch it again just for fun without me pausing. So we're scanning more positive. We get the anodic wave. We have iron 2 reduced to iron 3. We reach the stopping potential and turn around. We start to change the thermodynamics. We start to reduce the iron 3 that's accumulated at the electrode back to iron 2. And then that diffuses slowly away from the electrode. So this explains the shape of an ideal cyclic voltammogram, of an electrochemically reversible process. If in real life you see a cyclic voltammogram that looks like this, you are very, very lucky. Very few of us ever have CVs that look like that. So switching back to the PowerPoint. What are the situations in which we can deviate from this ideal electron transfer? Essentially, it comes down to a few factors, the primary of which being the reversibility of the electrochemical reaction. So if I say a electrochemical reaction is electrochemically reversible, what I mean is that this electron transfer occurs either infinitely fast or very quickly without subsequent chemical reactions. And so looking something like this, and that's why we look at ferricyanide or ferrocene as model systems because the geometric rearrangement when the electron is transferred is very small. If we have some other species where there is a large change in geometry, that often is then electrochemically irreversible. And there's a few cases where this could occur. One of them is where the electron transfer occurs and then there's a subsequent chemical reaction. Most of us who work in catalysis see kinetics like this, where you have an electron transfer to your catalyst. Your catalyst then undergoes some desirable or undesirable chemical reaction, and then you do not observe electrochemically reversible electron transfer kinetics. Another one is that if it's just very slow, for example, a large rearrangement in the geometry of your species when the electron is transferred. Now, most of us will see something somewhere in between. So we call these electrochemically quasi-reversible. So if you have peaks that are separated by, let's say, 70 millivolts instead of 59, okay, maybe that's quasi-reversible. So other considerations that we should take into account when we're studying cyclic voltammetry is the double layer charging and the uncompensated solution resistance. So as we know, ions will migrate when we change the electric field, but in cyclic voltammetry, we are constantly changing the electric field because we're constantly changing the electrode, or the electrochemical potential of the electrode. We're constantly changing that potential, and we're constantly changing the electric field. And the way that practically looks in cyclic voltammetry is it creates a kind of box. And so this is an example where there is no capacitance. And this is an example where there's very small capacitance, 15 microfarads. You hardly see anything. Okay, we get to 150 microfarads. Now we're starting to see something here. You see this background current that occurs here even prior to the addition of the wave. And oftentimes this can be used to estimate areas. If we go a little bit further, we look at 1.5 millifarads, we see this huge box, right? And so this double layer charging occurs here that again adds linearly with the Faradaic current, and then we have this box-like feature. Now the solution resistance is important because all of us will experience it to some degree. If we're in aqueous solutions, it's typically small, maybe 8 ohms, maybe 3 ohms or something like that. But if you are in non-aqueous solutions, it might be quite high, and it's something that needs to be considered. So while the solution has an added electrolyte, which increases the conductivity of it, there is some resistance associated with it. And so between the working electrode and the counter electrode is the solution resistance. That is, we have to have charged species passing between the two electrodes, and that has some associated resistance of the ion movement through solution. But in the ideal case, we measure the working electrode and the reference electrode very close together, kind of as I've shown here. A bulk of the solution resistance is accounted for by having these close in physical proximity to one another. So if you're doing an experiment, you want your working electrode and reference electrode to be as near each other as possible. And yet still there is some resistance between the working electrode and the reference electrode that is unaccounted for. And we call that the uncompensated solution resistance. This resistance causes a voltage drop following Ohm's law related to the amount of current and the resistance that is in the solution. And there is a voltage drop of what we apply versus what is actually apparent at the surface of the electrode. So if you think about it, if you have a resistive material and you apply a high voltage, that electric field is blocked to some degree. Practically, what that looks like when we do a cyclic voltammogram, that says 0 microfarads, but it's also 0 ohms. If we add 10 ohms, very, very slight distortion. We can see the original purple shown here, and the blue has moved a little bit more in the oxidative direction there and a little bit more in the reductive direction there. And what that practically, what we practically measure that is a change in the delta E peaks. So normally it's 59 millivolts, now it's slightly wider. If we look at 100 ohms, we can start to see a significant distortion in the cyclic voltammogram. If you're working in a non-aqueous solution, that might be typical. Or if you work in benzene, maybe you get somewhere where 1,000 ohms, and you probably can't get any meaningful data out of that. So again, the idea here is to minimize this uncompensated solution resistance, but also be aware of it. There are techniques for measuring this. Electrochemical impedance spectroscopy being my personal favorite way to measure that. And the last thing I want to point out today, before I give you guys the exercises, is that there's oftentimes confusion in cyclic voltammetry because there are two conventions for plotting CVs. There is the IUPAC convention shown here, where more positive potentials are shown to the right, and oxidative current is shown up. So then more negative potentials are shown to the left, and reductive current is shown down. Now, I am from the United States, but I'm not actually happy about this. The United States has their own convention that is often used, where more positive potentials are shown to the left, oxidative current is shown down, more negative potentials are shown to the right, and reductive current is shown up. There's historical reasons for this, basically because the first electrochemists were using mercury electrodes, and they couldn't study many oxidative reactions because when they did oxidative reactions, the background flow from oxidation of mercury was higher than any other redox species. So they did all of their early electrochemistry on reductions. And so they put it in the upper right in the first quadrant. But you'll see both of these. I personally use IUPAC. But if you're looking at a CV in a paper, make sure that you get your orientation right before you start making any conclusions. So here's the homework or the exercises. I'll send this out in a Word document, and as I mentioned, I'll send out the slides. The first one is basically a potential step. You'll make a plot similar to what I showed earlier. And then for linear sweep voltammetry, you'll look at different scan rates. You'll plot the double layer capacitance or determine the double layer capacitance at each of these scan rates. You'll predict the peak Faradaic current for all of those. I have a little hint here. And you'll compare the ratios of those. And you'll notice that you can't do too fast of scan rates because eventually your double layer capacitance will swamp out your signal from the Faradaic charge transfer. And that has implications for Faraday or for the use of microelectrodes. And so we can kind of talk a little bit more about that next week. Here are the topics that were most voted next week. I forgot to put electrochemical impedance as an option, but it's very valuable. So we'll talk about that next week, as well as both electrolysis and Faradaic efficiency. Both electrolysis would be more in the synthetic regime, or for those of us doing hydrogen production or water oxidation. as those are very, very important experiments. Electrochemical cell design, including H cells, U cells, the use of a membrane, converting between electrode reference potentials. I have a little trick that makes it easier conceptually, as well as a Excel program that will rapidly convert between reference electrodes, photochemistry for light-driven electrochemical reactions. We'll talk a little bit about junction potentials, and we'll talk a little bit about Tafel slope analysis. And then if anyone else has a topic that I didn't mention on there that you'd really like to cover, feel free to email me. I'll see if I can cover that as well. But with that, I'll leave it until next week. Thank you guys for coming. And I'll send out this stuff later today. So thank you.